In this video, let's review limits and continuity. If your limit approaches a number, first try to substitute directly. That usually won't work because it's just too easy. So your next step will be to factor and simplify and then substitute. So let's take a look at this first one. Can we just substitute? Yes. If I plug in -1 for my x value, I'll have, -1 squared plus 1, and that's going to give me 2. In the second example, if I do that direct substitution, that's going to give me 0 in the denominator, and so I can't just do that. Hopefully you recognize the numerator is your difference of squares, and so this is the limit as x approaches -1 of x plus 1, x minus 1, and that's all divided by x plus 1. We can see we have a common factor in the numerator and the denominator. So I factored and I've simplified. Now I'm going to go ahead and substitute. So this is the limit as x approaches -1 of x minus 1, which equals -1 minus 1, which is -2. In the third example, again, direct substitution won't work because that'll give us 0 in the denominator. Let's go ahead and factor the numerator, see if we can cancel a common factor. So this is the limit as x approaches 2. If I factor the numerator, let's see, two numbers that multiply to get -6 and add to get 1. That's going to give me x plus 3, x minus 2. Again, we have a common factor. I'll cancel the factor. And I've got the limit as x approaches 2 of x plus 3. And that's going to give me, 2 plus 3 is 5. If your limit approaches positive or negative infinity, we use spit in the ocean. What we need to do is just simplify the fraction down to the leading term in the numerator over the leading term in the denominator and reduce. And then we can evaluate as x approaches positive and negative infinity. And reason out what happens as x gets very large or very small. So let's take a look at this first one. If we reduce this down to just the leading term in the numerator and the denominator, I'll have the limit as x approaches infinity of, 10x squared over x to the 4th, the leading term in the denominator. Let's go ahead and reduce. And let's see, I'll cancel an x squared, so I'll have 10 over x squared. If our denominator grows without bounds and our numerator stays constant, this is going to approach 0. Let me just show you what I'm talking about. If I have a function 1 over 10, 1/10, if I increase the denominator to 1/100th, to 1/1000th, we can see that this, to 1/10,000th, this is all approaching 0. In the second example, I've made a little change. Notice I took the exponent off of the 6x cubed. Just leave that as a 1. Because what I want to take a look at now is if we reduce this down to the leading term in the numerator over the leading term in the denominator, my numerator is going to be the bigger. And so the limit as x approaches infinity of 3x cubed over -5x squared. Let's cancel an x squared. So this is the limit as x approaches infinity of 3x over -5. Now this time my numerator is going to grow without bounds. If your numerator grows and your denominator stays constant, this approaches infinity. In the next example, let's see, we've got leading terms in the numerator and the denominator. So I've got the limit as x approaches infinity of 4x squared over 2x cubed. Let's go ahead and reduce a 2 and an x squared. How about just 2 over x? And again, that's just kind of like that first example. That's going to go to 0. And in the last example, let's see, here's my leading term. Sometimes they're not in order, so just be aware of that. X approaches infinity of -5x squared over 4x squared. This time we have that common factor, x squared, cancel that. And this is just going to end up with, -5/4. All right, so the next thing that we're going to look at is the derivative as a limit. This, hopefully, you recognize as the definition of the derivative, this guy right here, as h approaches 0, of f of x plus h minus f of x over h. So here are some steps to solving these. We need to determine the function in terms of x, then calculate the derivative, and then evaluate at that particular value. So in this first example, that particular value is, well, 1/2. All right. Try to not look at this second term in each of these problems. See if you can determine the function just with this first term. So it looks like this function is just, well, f of x is equal to 4x to the 5th. So then we do the derivative of this, which would give you 20x to the 4th, and we evaluate that derivative at that x value of 1/2. So 1/2 to the 4th is 1/16, and so this is going to give me 20 over 16. If you want to reduce, you can. All right, in the second example, we've got our function, f of x, is just going to give me, well, x cubed. F prime of x is going to be, well, 3x squared. My x value in this one is just x. So I'm done at this point with this example. One more example. My function, f of x, is just going to give me the square root of x. F prime of x, well, actually, I'm going to go ahead and rewrite this as x to the 1/2. It's easier for me to see this when I apply the power rule. So 1/2 x to the negative half, and then evaluate that derivative at our x value, which is 9. Okay, so let's see, I'm going to have 1/2, and then I'm going to go ahead and move the 9 into the denominator and raise it to the positive 1/2, or take the square root. And so this is going to give me, well, 1/3 times 1/2 is 1/6, and that one's done. All right, so graphically looking at limits, it says a limit exists at a number if the limit as x approaches c from the left of the function is equal to the limit as x approaches c from the right of the function. Now, a function is continuous if the limit exists and the function evaluated is equal to the limit. Now, a derivative exists at a point if the function is continuous and the derivative from the left equals the derivative from the right. Let's look at some examples. So this one's asking us to evaluate the limit as x approaches 2 of the function. So we need to check the left side and the right side. If these both approach the same y value, well, then that's our limit. In this case, they do both approach 3. And so that's the limit as x approaches 2. In the next example, it's asking us just about a left-sided limit, this little minus sign here. So we're looking at as x approaches 0 from the left. So here's the left side of my curve. As I approach an x value of 0, I can see that my y value is approaching -2. The next problem is asking me what the function is at 2. Well, at an x value of 2, my function's defined as 1. Now, the limit as x approaches infinity, that means we're moving all the way to the right. If I look at my function, here's from the left, and we'll keep going to the right, I can see that it looks like we've got a horizontal asymptote, an in-behavior asymptote at 0. And so I'm going to say that my limit as x approaches infinity, the very right side of my graph, is going to approach 0. What is the limit as x approaches 0? The next example. We need to check both sides. So the left-sided limit is approaching an x value of, a y value of -2. And the right side, as x approaches 0, is approaching 0. And so in this case, it does not exist. The left and the right side have to be the same, and they have to equal a number. The limit as x approaches 0 from the right, we're just looking at a right-sided limit. So from the right side, as we approach 0, it's going to equal 0. And then the very last problem, the limit as x approaches -infinity, so we want to go all the way to the left of the graph. It looks like we have this horizontal asymptote at -1, so I'm going to say that my y value is going to approach -1. The last thing we'll look at today is the intermediate value theorem. And here's the definition. If f of c is between f of a and f of b, then there exists a point c f of c somewhere on the graph of f such that c is between a and b. Okay, so let's justify this function. I'm going to, instead of trying to show you a graph of the definition, let's just work through this problem first. So if I want to justify that the function has at least one root, and a root is where our y value is equal to 0. It's an x-intercept. And we're looking at between x values of 1 and 0. And so I need to evaluate, well, what is my function at 0? If I substituted 0 into my function, I would have 0 squared plus 3 times 0 minus 2, which is negative 2. That point on my graph is 0, negative 2, right here. Now, f of 1, we'll substitute it in. That would give me 1 plus 3 would be 4 minus 2 is 2. So at an x value of 1, I've got a y value of 2. So my graph, and I don't know what the other behavior is, but from between these 2 points, I'm going from a y value of negative 2 to a y value of positive 2. So I know somewhere in between, I have to have a root. And so showing this is my justification that there is a root between an x value of 0 and 1.